All right, so we didn't finish chapter 1 yesterday, so we're going to finish chapter 1 today and hopefully do chapter 2. I think 3 is way too ambitious, but hopefully we can finish those 2 today. All right, so we're going to talk just a little bit today about some of the, actually, let me use back, we'll just start off with some really simple sort of equations for electrochemistry. And so the first one that you have to remember is that current is equal to dq dt. So remember, Q is charge and T is time. So again, the change in charge over time gives you current. And you need to, again, this is something you can take electronics, it's the same definition, but you got to kind of remember, you can go back and forth between current and charge, but it's usually in the kind of like an integral, right? You integrate this to get back. That's a charge. We talked a little bit about Faraday's law yesterday. Here, let's write it out in equation format. So the charge divided by, this is the number of electrons, has this Faraday's constant, is equal to N, and N is the number of moles that has reacted, right? So again, we talked about the fact that electrochemistry is quantitative. This is, that's in the camera. This is the reaction that sort of tells you that. So the number of moles that react, that are oxidized or reduced, is equal to whatever the charge is divided by the number of electrons, and Faraday's constant. So you can go back and forth then, because you know Q played I. You can look at all of that, and so if you would put those together, the change in the number of moles over time would be I divided by NF. So again, change in moles over time relates kind of back to current. Now, in electrochemistry, again, it's a junction method. Everything happens at the junction between the electrode and the surface. And so we really care about the area of the electrode because that tells us how much surface we have to do a reaction. And so people almost always talk about the rate of reaction, and that rate is usually has the surface area of the electrode in it. So the surface area of the electrode, then they correct it for the size of the electrode. So that way you could look at the rate of the reaction of 2 different electrodes that were different sizes, and you could actually compare them. Sometimes people will even look at this I over A, call that J, which is a current density. As we look along. Okay, so those are some just simple equations coming out of Faraday's law of sort of the rate of a reaction, as I said, usually with a surface rate per area. Sort of looking at that. Again, yesterday we talked about overpotential. Nice, Greek letter eta. And so overpotential is defined as whatever you're applying minus equilibrium. Whatever you have to apply, you have to work minus whatever you should have to apply the E in equilibrium. And again, it tells you about how much you depart from that equilibrium potential. So again, how much you're away from kind of what the ideal potential would be. Okay, and then they have a couple other random things. I think even when I read like the freshman or the sophomore level chemistry textbooks, they always are talking about 2 types of electrodes. And again, I don't think these electrodes really ever come up in our own studies. But because they're kind of part of the electrochemistry knowledge, I think we should do that. So they always give 2 examples of electrodes in this is an I versus B plot. And so they'll talk about the ideal non-polarizable electrode and the ideal polarizable electrode. And basically, let's start down here. So for the ideal polarizable electrode, the idea is that even though you're polarizing it, even though you're polarizing it, you're essentially getting no change in current over a wide kind of width of time. So you can apply a potential and you don't get any change in time. So basically, no change in current with a change in voltage. That's the ideal polarizable electrode. The ideal non-polarizable electrode then is the opposite. So an ideal non-polarizable electrode looks something like this, apart from the ideal at the end. So the ideal part, right, is that. The straight line part, the ideal. And eventually, everything has to be non-ideal. So the ideal non-polarizable electrode is this. So we get no change in voltage with a change in current. So these are the two types of electrodes you could have. Okay, so we've defined them, and as I said, we don't usually use these terms in our lab, so you say, why do I care? But it's to kind of think about what kind of electrode we would want in each situation in our lab. So we have two choices, non-polarizable or polarizable. And so which one do you think would be the best reference electrode? So we're looking at, do we want this one to be our reference electrode? Do we want no change in voltage with change in current? Or do we want this one to be our reference electrode? All right, we'll do a show of hands again on camera so no one will see you. How many people vote for the top one, non-polarizable, for a reference electrode? Come on, you don't be afraid to vote if you want to. Come on, Kate. I called you out, sorry. All right, and then how many people think this one would be the best reference electrode? Okay, well, Kate was right. So I didn't call her out in the back. So this top one, check with is what you want. So what we talked about yesterday with reference electrodes, we said that even if we want there to be a constant voltage, right, no matter what. So this one, it doesn't matter if I'm down here with current or down there with current, right, I get a constant voltage. So again, I went through this because it's obviously, you can put up these graphs and then they're hard to interpret, right? But with a reference electrode, right, we would want out, basically, right, we want a steady voltage. No matter what we kind of do to it, right, we want to always have it be the same voltage. So that's why this one is the best reference electrode. And so you'll read that, I think in the textbook it might say that. The best reference electrode would be, the best reference electrode would be an ideal non-polarizable electrode. And again, with all that gibberish, it kind of just goes, but it means the same thing that we said yesterday. You want a steady voltage, and that's what you do here. Okay, so now this is the easier part. Which one then do you think you would want to use as your working electrode? All right, we'll take a vote. How many people are going to vote for the non-polarizable electrode? How many people are going to vote for the polarizable electrode? All right, you're getting the gist, right, that you just vote the opposite. I do this in my class all the time. Like the second vote is always easier. All right, right, so for the working electrode, what we often talk about is what we call like a working range. And that's simply the potentials that you can scan to on that electrode without getting some side reaction from the solvent that you don't want, like water oxidation, or yesterday we learned about hydrogen reduction, production of hydrogen by reduction of H+, right? So we want electrodes usually with a large working range, so we would like there to be no change in current as we go along at different voltages. But again, I'm trying to show you these, weird things that you see in the textbook have real application to what we do in our electrode. All right. We'll be croaking forever on the video tape. Yesterday's lecture didn't.
Okay. So now we're going to go and do a diagram. It kind of goes with the chart we did yesterday. I'm sorry that the chart we did with the diagram. We're going to talk about factors that affect the electrode reaction rate, and the current. So we went over a whole bunch of factors yesterday, but I'm going to summarize for you. All right, you have to know this is my ultimate favorite diagram. Like, and I'm not kidding that when people pull this out with their oral exam, it does them very well. Because it allows you to explain different parts of the process in a diagram that looks like you know what you're doing. Okay, it's not spontaneous. I know it's not spontaneous when you put it up, but the rest of them don't know that you didn't just make this up, kind of thing. And the reason it's my favorite diagram is that it puts together a lot of the processes that we are going to be talking about. So what are those processes? We're going to be talking about mass transfer. How does it get to the surface? We're going to be talking about absorption. And anyone in our lab knows we just love to talk about absorption in our lab. And finally, electron transfer. So again, that's my electrode coming in, and we're going to talk about our species kind of sitting out here in solution. Right? And in order to get to the electrode, O must wander, right? It must have some sort of mass transfer to get over here near the electrode surface. Once O gets to the electrode surface, it can absorb. So that's how it will absorb to the electrode surface. And then, right on the surface, once it's on the surface, that right there, go the other way, right? We can undergo electron transfer, right, and become R's. As a reaction. All right, so you add electrons, it becomes R, right? Then R can desorb from the surface. It just becomes R out there, right? And then it can get away from the surface again by mass transfer. I think the one in the book might put a couple of chemical reactions in there too. I like them out of mine. We'll talk about them in a minute. So I really like this diagram again because it's one thing to say, well, there's three things that come into play. We're going to talk kinetics, right? Because the answer is how fast your electrochemistry reaction can be depends on which one of these is the slow step, right? So this is not any different than any other kinetics, right, that you've ever been taught in chemistry, right? There's always the slow step, that's the rate controlling step. And so in this case, right, there's a rate, some sort of rate of mass transfer, there's a rate of absorption, there's a rate constant of some sort for electron transfer. We can get rates for all of these things. So there's rates for all of those. And which one controls the process depends on which one is the slowest. So in our lab, we'll talk about absorption and diffusion on other days more. But the thing is that when you're talking to somebody, particularly another professor that doesn't do electrochemistry all the time, the textbook things will all assume that this is the rate limiting step. So this is the slow step, that's the rate limiting step. And so, we'll have to go many, many, many chapters into the textbook before we won't make that assumption. So that's the assumption that everybody who's ever taught a little electrochemistry, MP Chem or General Chem, is taught to make, that the slow thing is getting this thing to the electrode. However, in our lab, what's the slow step? Absorption, right? So at our carbon fiber microelectrodes, this is the slow step. So a lot of times, if you're in your orals and you have some, lovely P-Chem professor asking you questions, again, all they've ever taught is this. And so when you're like, no, that doesn't matter, then that doesn't make sense to them why it doesn't matter. But then you throw up a diagram like this and you say, well, these are the things that could matter. And it turns out that absorption is the key here. That absorption is the slow step. and we don't do the electron transfer unless it absorbs. So it gives you a way to put into context, rather than just kind of being like diffusion, I don't know, it's all absorption, kind of thing. It shows that you know all the processes that could be there, and then you're going to tell them, go on from there and tell them which ones are more important. So again, I've seen people use this before and quite successfully, look at that. And so I really like this diagram, like a lot. I'm not kidding, that it can be used. Okay. I know, we're still in chapter 1. I told you chapter 1 was a monster. All right, so we're going to talk a little bit now about IR drop and resistance. Right, and so this IR drop basically is that you get a voltage drop in your solution to current passing through the resistive solution. So every solution is going to have a resistance, a solution resistance. And so you'd like that to be low. So how do you keep the solution resistance low? Concentration of ions, right? So this is dependent on that electrolyte concentration. Again, we hardly think about it because we don't change it in our lab. But a lot of people who develop batteries and that kind of stuff really do think about this stuff. And so someone may ask you about your resistance or why you don't care, that kind of thing. And so you need to think about that. Right, and so what that means is that E measured, right, is really going to be E applied minus IR. So whatever your electrode actually sees is not quite what you applied, because some of that voltage, again, is dropped in the solution. And again, people will also call this ohmic drop, right? Ohm's law is V is equal to I. That's ohmic drop. So we, in electrochemistry, people typically get around that by, using 3 electrodes. So we've already talked about the working electrode, right? That's where a Faraday process takes place. We've talked about the reference electrode, right? And the purpose of the reference electrode is to measure voltage between this and the working electrode. So that's your voltage reference. That's what reference means. So we haven't talked about the third electrode. And the third electrode is either called an auxiliary electrode or a counter electrode, either or. In this case, this is an electrode to pass current. Take my class box to show you the 3 electrode potentiostat. For today, we're just going to do this diagram. So you have your working electrode here, reference electrode here, and say our auxiliary electrode over here. So if we were to plot potential on this axis, there'd be a little bit of a drop between the working electrode and the reference electrode due to, solution resistance there. And then there'd be more of a drop, because I keep them further apart, right, between the reference and the auxiliary. But it turns out that your circuit can compensate for this drop. So none of this drop counts. Again, I'm going to spare your circuits today. But it's in the feedback loop, it's compensated for. This, however, is not compensated for, so those are usually uncompensated. So this part counts. So whatever the solution drop is between your working electrode and your reference electrode, that's never compensated for. There's always an I. So what does that mean? How do you want to place your reference electrode and your working electrode in this? Close, right? So that means you want your working electrode and your reference to be close. And then when people design electrochemical cells, they often put the third electrode just wherever. It doesn't matter. It's already compensated for, so it can be far away. I don't care. All kind of thing. Like they would design it to make them very close there. Okay, so that's our textbook electrochemistry lesson. So yes, once again, we're going to ask ourselves, why do we not use 3 electrodes in the Benton lab? I just told you that everybody else does. Why don't we do it? So let's think about the reasoning for a minute. So what's IR count? There's only 2 variables, I and R. Okay, so we got 2 choices as to which variable is important, because there's only 2 variables. So what do you think the solution resistance is? Anyone want to give a guess as to the resistance of a highly ionic solution? Again, I'll take an order of magnitude. All right, resistance is in ohms. What are we looking at? 10. I was going to say 10 sounds like a great guess to me. Certainly not more than 100, right? I mean, it's not very resistant. So, I don't know. We'll say, it's in the range of like 10 ohms. That's not much. And, again, because we don't play with the electrolyte, I don't think that's our big advantage. What's I? Everybody should be able to answer this question. What's a typical current that you measure in your 1 nanoamp? Let's go with it. I'm looking for order of magnitude, right? Amps. We'll go with that. Something like that. So